In this video, we will use LINEST function and matrix solution for linear polynomial regression of this dataset, the x and y. We begin with the chart, and we use scatter chart. And we generate the polynomial trend line. We use polynomial raised to the power 2 and use the equations label and show the r squared. So here we have the trend line equation, which is y equals 9.38 minus 1.68x plus 0.551x squared, because this is the second degree polynomial. And our fitness of the curve is 0.985, which is the r squared. We will calculate these values using LINEST and matrix. So this is our B0, B1, and B2. B0 is 9.38, B1 is negative 1.68, and B2 is 0.551. We will use this equation where y equals B1, the matrix of x, that's 1 comma x1 x comma x squared, times B0 semicolon B1 semicolon B2. So we factor out the coefficients B0 in this matrix. So we begin with filling up this matrix, the 1 comma x matrix, which is RA formula of the x values raised to the power 1 or raised to the power 0. And the x column will be RA formula of the x values raised to the power 1. And the x squared column will be RA formula of the x values raised to the power 2. So we have the 1 comma x matrix. Now we can calculate the LINEST. So it is LINEST will be LINEST data y and data x. And we show the full statistics. So our B0 is 9.38, matches to our chart. B1 is negative 1.676, rounded was negative 1.68. Our B2 is 0.5509, rounded was 0.551. We will calculate each value of each output of this LINEST using matrix solution. We begin with the P-Jorina inverse, which is minverse M mult transpose of this matrix and itself. And the P-Jorina cofactor, which is M mult transpose of this matrix and the y values. Now that we have these two matrices, we can calculate the coefficients, which is M mult of the P-Jorina inverse and the P-Jorina cofactor. So we have B0 matches to our B0 in the LINEST, our LINEST output. Our B1 matches to our LINEST output. And B2 also matches to our LINEST output. And these output also match to our chart, but they're rounded off. 9.38 for B1, negative 1.68 for B2, and 0.551 for B2. That one is B1 and B2. Now we can calculate the estimated y using this equation. This matrix times this matrix. So this matrix multiplied with this matrix will give you the estimated y. So M mult of this matrix and the coefficients. Now that we have the estimated y, we can calculate the residual sum of squares, which is equal to sum x my, sum of squares of difference of y and y hat. Y and y hat, or estimated y. 11.27 matches to our LINEST output. Then we calculate for the degrees of freedom. We begin with the rows. So n is the number of rows of range. So this is the rows. There are 9. So our DFD, degrees of freedom, is rows minus columns of the range 6. And this DFD matches to our LINEST output. Our stay x, which is equal to the square root of the residual sum of square divided by degrees of freedom. 1.37 matches to our LINEST output. Next, we calculate for the standard errors. Here we have stay x times square root of p 1. 1.808 matches to our LINEST output. And our standard error value for B1, which is stay x times square root of stay x times square root of p 2. 0.80961 matches to our LINEST output. Then the standard error value B2, which is again stay x times square root of p 3. 0.0805 matches to our LINEST output. Next, we calculate for the total sum of square, which is n times variance of population y. So n, the population, times variance of the population y. 753. So we calculate for regression sum of square, which is total sum of square minus residual sum of square. 742.437 matches to our LINEST output. Next, we calculate for the F statistic, which is equal to ESS, residual sum of square, divided by 2. 2 because there are now 2 independent variables, divided by stay x. And this is divided by stay x squared. So 197.62 matches to our LINEST output. And R squared. This is equal to ESS, regression sum of square, divided by total sum of square. 0.985 matches to our LINEST output and our chart. This completes the use of LINEST and Matrix Solution for linear polynomial regression of the second degree.